Left, a city street in Shanghai. Right, an 85-year-old building walking across it.
Faster!
Not rolled, not towed.
It's
Walking.
collapsing!
7,500 tons. 190, 8 mechanical legs. 60, 2 meters of travel. 18 days. 7,500 tons is 15 fully loaded Boeing 747s. Stacked into one concrete box and told to move. The demolition permit was already drafted. One engineer put it simply. We were told to knock it down. We asked for 1 month to try something else. Expert, because if the legs go out of sync, the building cracks. Not settles. Cracks. An 85-year-old masonry frame has no tolerance for twist. 2 millimeters of differential lift and the walls start to split. Now watch what they actually built. Shanghai. Huangpu District. One of the densest urban cores on Earth. 24 million people. Land here trades for more than gold by the square meter, and in the middle of a planned commercial redevelopment sits a problem. Lagena Primary School. Built in 1935. 5 stories. Brick and concrete. T-shaped in plan. A protected historical structure. Which means it cannot legally be demolished, and it sits directly on top of the new development footprint. The plan calls for a shopping and office complex. 2 underground levels. Excavation to 15 meters. The school is standing exactly where the hole needs to go. Move the development. The economics collapse. Demolish the school. The law forbids it. Leave it in place. The excavation undermines the foundation. 3 options. All dead. So the question becomes something else entirely. How do you move an entire building without taking it apart? Building relocation is not new. America moved lighthouses. Europe moved churches. The standard method is track sliding. Cut the building free. Set it on steel rails. Push it with hydraulic jacks. It works. In a straight line. That is the entire problem. Because this building does not need to travel in a straight line. The new site is 62 meters away and 21 degrees off axis. The building has to move forward. Then rotate. Rails cannot turn. You would need to lay a second track system. Lower the building. Re-cut. Re-lift. Every set down is a chance to crack an 85-year-old wall. There is a second problem. Worse. The site is not flat. Shanghai is built on soft alluvial clay. The Yangtze Delta laid it down over 10,000 years. Water content above 40% in the upper layers. It compresses under load, unevenly. Put 500 tons on a rail across that ground and the rail deflects. The building follows the rail, and the frame twists. A senior structural engineer on the project. Old masonry doesn't fail from weight. It fails from geometry. Bend it 2 millimeters and it tells you. Expert. So the team throws out the rails and proposes something that sounds absurd. Give the building legs, not wheels. Legs. Each one able to lift, step, plant, and push independently. A machine that walks. Carrying a 5-story school on its back. Nobody had ever done it at this scale. Chapter 1. The survey. Before you lift anything, you need to know what you are lifting. The 1935 drawings are incomplete. 85 years of renovations were never documented. Walls added. Walls removed. Nobody kept records. So the team scans the whole building. 3D laser scanning. Millimeter resolution. Every wall. Every column. Every crack. Hundreds of millions of points. They build a digital twin. Problem. A point cloud shows shape, not strength. You cannot see inside a brick wall with a laser. Fix. Core sampling. Drill cores from the columns. Test them in a lab. Rebound hammer testing on every load, bearing element. The concrete comes back weaker than modern grade, as expected for 1935. Now they know the real numbers. Next problem. The building is not symmetric. T Shaped plan. The stem is heavier than the wings. Load distribution is uneven across the footprint. Lift it evenly and you overload one side. Fix. Model the mass distribution first. Then place the legs where the load actually is, not where the grid says. Dense clusters under the stem. Sparser under the wings. The leg layout is not a grid. It is a map of the building's weight. Chapter 2. Reinforcement. Here is the uncomfortable truth about old buildings. They are designed to sit still, gravity down, foundation up. That is the only load path they know. Moving introduces something new. Horizontal force. Acceleration. Deceleration. Rotation. The 1935 frame was never asked to resist any of it. So before the building moves, they make it stronger. Carbon fiber wrapping on the critical columns. Steel bracing through the interior. Grout injection into every masonry void they can find. Problem. Injecting grout at high pressure can split old brick. The mortar from 1935 is soft. It gives before the brick does. Fix. Low pressure injection. Slow. Let the grout find the voids by gravity and capillary action. It takes weeks instead of days. Nothing splits. Then the windows. Every pane braced or removed. Glass is the first thing to go when a frame flexes. Interior partitions get temporary props. The building is turned into a single rigid box. Because a rigid box can be lifted, a loose one cannot. Watch what comes next. Chapter 3. The cut. This is the moment of no return. To move the building, you have to separate it from its own foundation. Cut the connection that has held it up for 85 years. But you cannot cut it all at once. Cut everything and the building drops. So they go in stages. First, excavate a working trench around the perimeter. Then tunnel underneath in narrow strips. Never more than a fraction of the footprint, open at one time. Into each strip goes a steel transfer beam. Problem. A steel beam under a wall carries nothing until it is tight. A gap of even a few millimeters means the wall is still hanging on the old foundation. Fix. High. Strength grout packed into every gap. Then wedges driven in from both sides. Preload the beam before it is asked to carry anything. Strip by strip, the beams go in. Longitudinal beams under the walls. Transverse beams tying them together. A steel grillage forms under the entire building. Engineers call it a chassis, because that is exactly what it is. A reinforced concrete and steel raft. The building no longer sits on the ground. It sits on a machine. The site engineer describing that week. The day we cut the last column, nobody spoke.
Nothing moved.
Everyone just watched the gauges. Expert. The gauges did not move. The chassis held. Chapter 4.
Nothing moved.
The legs. 190, 8 of them. Each one is a hydraulic robot. A vertical jack. A horizontal jack. A foot pad. A sensor package. Here is how one leg works. Vertical jack extends. The foot presses into the ground. The leg now carries its share of the load. Horizontal jack extends. It pushes the chassis forward. Vertical jack retracts. The foot lifts. Horizontal jack retracts. The leg swings forward to a new position. Plant. Push. Lift. Swing. That is a step. Now do it 198 times at once. Except you cannot. Problem. If every leg lifts at the same moment, nothing is holding the building. 500 tons in free fall. Fix. Split the legs into groups. Half planted. Half stepping. Always. Exactly how a walking insect stays stable. The engineers borrowed the gate from biology. But biology does not have to worry about masonry. Next problem. Load transfer. When one group lifts, its load has to go somewhere. It goes to the planted group, which means those legs suddenly carry double. Fix. Every leg is rated for well over its share, and the transfer is done in ramps, not steps. Pressure bleeds from one group to the other over seconds. The building never feels a jolt. Chapter 5. The brain. 1 in 98 legs cannot be run by hand. Every leg reports to a central computer. Pressure, displacement, tilt. Hundreds of data channels, sampled continuously. The system holds every leg to a shared reference plane. If one leg is high, it bleeds pressure. If one leg is low, it pumps. Correction happens faster than the structure can respond. That is the whole trick. You are not moving a building. You are holding a plane perfectly flat and translating it. Tolerance across the entire footprint. Within a few millimeters. A control engineer on the project. The building doesn't know it's moving. That's the goal. If it knows, we've failed. Expert. Problem. Soft Shanghai clay does not push back evenly. One leg lands on a firm patch. It takes more load. The next lands on soft ground. It sinks. Fix. Build a temporary reinforced track bed across the whole travel path. Soil improvement first. Then a concrete working slab. The legs never touch native soil. They walk on a purpose-built road. Next problem. The slab still deflects under 500 tons. Not much, but enough to matter. Fix. The control system stops trusting the ground entirely. It measures the building, not the road. Sensors reference the chassis itself. If the road sags, the legs simply extend more. The building stays flat regardless of what is underneath it. Some results were unexpected. Chapter 6. The first step. They do not go 62 meters on day 1. They go a few centimeters. Then stop. And measure everything. Crack gauges on every monitored wall. Tilt sensors on every floor. Nothing has opened. Nothing has shifted. So they go again. The building moves at roughly 10 meters per day. That is about half a centimeter per minute. Slower than a minute hand. Stand next to it and you cannot see motion. Come back in an hour and it is somewhere else. Slow is the entire point. Slow means low acceleration. Low acceleration means almost no horizontal force on the frame. Speed is what kills old buildings. Chapter 7. The turn. This is the part rails could never do. The building has to rotate 21 degrees to fit the new site geometry. Problem. In a rotation, every leg travels a different distance. Legs on the outside of the arc move far. Legs near the pivot barely move at all. Give them all the same stroke, and the building tears itself apart. Fix. Every leg gets its own individual step length, calculated from its exact radius to the pivot point. 198 different stroke commands. Every single cycle. And every leg foot also has to swivel. Because on a curve, the direction of travel changes leg to leg. The whole array becomes a single articulated machine. Curving a 5-story building through open air. An engineer watching the rotation. Straight, line moving is arithmetic. Rotation is geometry. Every leg is solving a different problem. Expert. Chapter 8. Utilities. Easy to forget. A building is connected to the city. Water, power, drainage. All of it hard, piped into the ground. Move the building 62 meters and every connection shears. Fix. Disconnect everything before the move. Tap the lines. Seal the drains. Temporary flexible feeds run to the site for monitoring power only. Those feeds are on reels. They pay out as the building walks. Next problem. Buried services in the travel path. Old Shanghai ground is full of them. Many undocumented. A forgotten drain under the root collapses under 500 tons and takes a corner of the building down with it. Fix. Ground. Penetrating radar across the entire corridor. Then trial pits to confirm every hit by hand. Anything found is diverted or filled solid. The road is made boring on purpose. Chapter 9. Arrival. 18 days after the first step, The building reaches its new position. 62 meters translated. 21 degrees rotated. Now it has to come down. And this is where it could still go wrong. Problem. The new foundation is already built and waiting. Piles driven. Cap poured. Bearing points cast to exact elevations. The building has to land on all of them at once. Miss one by a few millimeters and that point carries nothing. Its load redistributes to the neighbors. Fix. Lower in stages. Millimeters at a time. Monitor pressure at every bearing point as the load arrives. Any point reading low gets shimmed and grouted before going further. The descent takes longer than some of the travel days. Then the permanent connection. The chassis is tied into the new foundation. Rebar coupled. Concrete poured. The steel that carried the building becomes part of it forever. Then the legs come out. 198 of them, unbolted. Craned away. The machine disappears. The building stays. Chapter 10. The inspection. Now the only question that matters. Did it survive? Crack gauges are read across every monitored wall. Levels are shot across every floor. The digital twin from the survey is compared to a fresh scan. Point by point, before against after. The structure holds. No structural cracking. No differential settlement outside tolerance. An 85-year-old masonry building walked 62 meters and turned 21 degrees, and arrived intact. The project engineer afterward. People ask if we were nervous. We were nervous for 2 years. The 18 days were the calm part. Expert. Then the excavators move in behind it. Where the school stood for 85 years, a 15-meter hole opens. 2 basement levels go in. The commercial complex gets built, and the school sits 62 meters away. Looking at it, both things happen. Nobody had to choose. That is the actual achievement. Not the 500 tons. Not the 198 legs. The idea that a growing city does not have to erase its own history to move forward. Because the alternative was a landfill. Shanghai has done this again since. Historic blocks lifted, rotated, set back down. Walking buildings are becoming a tool, not a stunt. And at the school itself, the strangest part is how ordinary it looks now. The brick facade is cleaned. The windows are back in. Trees are planted along the new frontage. People walk past it on their way to work.
Okay, go!
Kids ride scooters along the pavement outside. Someone parks a bike against the wall. None of them know the building is standing 62 meters from where it was born. It walked here, on 198 legs, and nobody can tell. That is what perfect engineering looks like. Invisible. If you want more impossible builds like this one, subscribe to Titan Build. And tell us in the comments which structure we should move next.